A few years ago, if someone told you that a computer would write code, answer questions, explain history, create content, and even help run businesses, most people would probably laugh. But today, that feels normal. Tools like ChatGPT, Gemini, Claude, and others are suddenly everywhere, and naturally, everyone is asking the same question. What exactly is a LLM? How does it work? And why does everyone suddenly care about it? Let's break it down. No hype, no complicated AI jargon, just simple explanations. Before we talk about LLMs, there's one idea we need to understand first. Foundation models. Think about humans. Before becoming a doctor, or engineer, or musician, people first learn general knowledge, language, patterns, how the world works. Then later, they specialize. Foundation models work in a similar way. Instead of training AI for one specific task, we train one huge model on massive amounts of general data, books, articles, websites, code, documents. The goal isn't teach one job. The goal is teach broad understanding. Then later, that same model can be adapted. Writing, coding, translation, chat, search, business automation. That broad base is called a foundation model, and one type of foundation model is a LLM. LLM stands for Large Language Model. Large because it learns from enormous amounts of data. Language because text is its primary interface. Model because underneath, it's mathematics. But honestly, that definition doesn't help much. So here's a simpler explanation. LLM is basically a machine that predicts what should come next. That's it. Sounds too simple, but that idea becomes surprisingly powerful. For example, if I say, the capital of France is, your brain already predicts Paris. You don't calculate, you predict. LLMs do something similar, not by understanding like humans, but by learning probabilities. What word is most likely to come next, then the next, then the next, again and again, very fast until it can reliably generate coherent sentences, and suddenly it looks intelligent. Now comes the interesting part. How do large language models actually work? At first glance, it feels almost magical. You type a question, a few seconds later, a complete answer appears. But underneath, there's a surprisingly structured process. Let's break it down. Modern LLMs work in roughly 4 stages: training, tokenization, transformers, and prediction. Let's go one by one. First, training. Before a LLM can answer anything, it needs to learn. And learning means consuming an enormous amount of data. Where does this data come from? Books, articles, research papers, public websites, code repositories, documentation, educational content, forums, and many other publicly available or licensed sources. We're talking about huge scale, not gigabytes, not terabytes, sometimes petabytes of data. Imagine reading millions of books. That's the scale. But there's another challenge. Training on this much data is extremely expensive. Your laptop CPU cannot realistically train modern LLMs. Even powerful desktop computers struggle. This is where GPU become important. GPU were originally built for graphics, but they turned out to be incredibly good at running millions of mathematical operations in parallel. Instead of calculating one thing at a time, GPU process thousands of calculations simultaneously. Modern AI training often uses thousands of GPU running together for weeks or even months. Now, what exactly does the model learn? This brings us to parameters. Parameters are one of the most important ideas in AI. Think of parameters as tiny adjustable values inside the model. These values slowly change during training. They store learned relationships, not facts, patterns. For example, suppose the model repeatedly sees The capital of France is Paris. After seeing similar examples many times, internal parameters start adjusting. Eventually, the model learns that words like France and Paris are strongly related. Modern models may contain billions or even hundreds of billions of these parameters. You can think of parameters as compressed statistical knowledge, not a database, not stored sentences, patterns. Now let's understand how training actually happens. Imagine we take a sentence, I love eating pizza. During training, we hide the next word, input, I love eating, expected output, pizza, the model predicts. Maybe it predicts burger. That prediction is wrong, so the model adjusts internal parameters slightly, then tries again, and again, and again. Now imagine repeating this process, not thousands, not millions, but trillions of times. Eventually, the model becomes very good at predicting missing text. That's training. Now comes tokenization. Computers do not understand words, they only understand numbers. So before text enters the model, it gets converted. For example, ChatGPT is amazing may become. These numeric IDs are called tokens. A token is usually not exactly one word. Sometimes one word becomes multiple tokens. For example, unbelievable might become unbelievable. This helps models work efficiently, but numeric IDs alone still have no meaning. So next, tokens become vectors. A vector is simply a list of numbers. Instead of storing cat, the model converts it into something like hundreds or thousands of numbers. Why? Because vectors allow meaning to emerge mathematically. Words with similar meaning end up closer together. For example, king, queen, man, woman. These relationships become visible in vector space. Now, all those vectors move into the transformer. This was the breakthrough behind modern LLMs before transformers. Models struggled with long context. Transformers introduced attention. Attention allows every word to look at other relevant words. For example, the animal didn't cross the street because it was tired. What does it mean? Animal? Street? Transformers calculate relationships and determine context, and they do this across entire paragraphs, not just nearby words. That's what makes modern conversation possible. And finally, prediction. This is the part users actually experience. Imagine you ask, suggest me some thriller books. The question gets converted into tokens. Tokens become vectors. Transformers process context, and then the model predicts the next token. Maybe you, then again, should then, again, read, then again. One prediction at a time. Each prediction uses probabilities. For example, 40%, the silent patient, 25%, Gone Girl, 15%, the girl with the dragon tattoo. The model chooses one, adds it to context, and predicts again. Repeat, 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 until the answer is complete. That's why responses can change, because underneath, LLMs are not retrieving fixed answers. They are generating answers, one prediction at a time. Now you might wonder, if all of them work similarly, why do we have so many models? ChatGPT, Gemini, Claude, Llama, Mistral, DeepSeek, and many more. Simple answer, different goals. Imagine asking, which vehicle is better? Bike, SUV, truck? Depends on the job. Same with LLMs. Some optimize for speed, some optimize for reasoning, some optimize for lower cost, some optimize for privacy, some optimize for enterprise. Different trade-offs create different models. Now, this is important. LLMs are impressive, but they are not magic. They can confidently say incorrect things. This is called hallucination. They may miss recent information. They don't truly understand the world like humans. They inherit biases, and running large models requires serious computing power, so treat them like smart assistants, not sources of absolute truth. Large language models may look magical, but underneath, they're systems trained to recognize patterns and predict language, and somehow, that simple idea is changing software forever.